So, differentiation from first principles. To briefly recap, we know that differentiation is a method that enables us to find rates of change, yeah?
Yeah.
And we have compared it with GCSE maths, where in order to find the gradient of a straight line, just a simple straight line, it's change in y over the change in x. Okay, we find 2 points along the line. We find the change in y, the change along the y-axis between those 2 points, and the change in the x-axis along those 2 points. And it's change in y over change in x. So the rate of change, the change in y over the change in x, or the rate of change of y with respect to x, and that will give you the gradient. Okay. Now, differentiation from first principles. For a straight line, we know that the gradient is constant. Once we find it at one place, it will be the same along the line for all time. For a curve, however, for example, y equals x squared, the gradient is constantly changing. So that doesn't mean that we can't find the gradient. It means rather we have to approximate the gradient. So let's look at this example, y equals x squared. So let me just draw that. Just draw that like so. And y equals x squared is simply this. And as you know, I'm a very poor artist. Okay, so this is y equals x squared. Yeah. Now, say we had a point. Say we had a point P. That clashes too much. Let's use orange. Say we had a point P,
Okay.
and that point P basically lay on the line like that. Yeah. So this is our point P. Now we can find the gradient easily on this line, because another definition of differentiation is that the gradient, by the way, this is very important for your later course, for your later modules in maths. This is very important. The gradient at point P is equivalent to the gradient of the tangent. So all you would need to do for this particular example is once again to find the change in y over the change in x, if you knew what they were. So what are we missing in order to find the change in y over the change in x?
Um, a second point.
Or
Uh,
even a third point. That's what we're missing. We're missing a point here. I'm going to call that y. Not y. I'm going to call that b. And we're missing a point there. I'm going to call that a. If you don't have those 2 points, then there's no way you would be able to find the gradient at the point P. So the caveat must have 2 points on the tangent in order to actually make this orange writing viable or practical. Since we don't have that, we need to do something else. Okay, we need to do something else. So I'm going to redraw this situation again with the y equals x squared. I'm going to redraw the situation again with the y equals x squared graph. So that's x, that's y, and this is our curve. And I'm going to have the point P once again. But this time, I have several other points. So I have point A, I have point B, and I have point C. And what I'm doing is that I'm basically drawing straight lines between P and these so-called points. Yep.
Yeah.
And what I'm basically doing is that I am drawing. If I know, we don't really know these points, but if we bring them very close to P. So first of all, what you would first of all do is that you would, we've got straight lines, right? We've got straight lines that pass, that are pretty much, well, almost tangential to the point P. So we have this one here. So from P to C, and then we have this one from P to B, and then we have this one here from P to A. These are badly drawn, so don't worry about that. The thing is, if our point gets closer and closer to P, we have a better chance of working out the gradient at P. So the problem with P to C is that it's basically not a tangent, yeah? The line PC is not a tangent. It's just a straight line that happens to cut through P. If we try and find the gradient of this tangent, we will be far away from the true gradient at P. Do you agree?
How?
Because it's not a tangent, so we need to go back again to this point here. Notice how this orange line here is a tangent.
Yeah.
It's a tangent to P, right? It's basically just touching the curve. It doesn't, well, as best as I could draw. It's not touching the curve. I mean, it's not crossing the curve. It's just touching the curve. It's just scraping the curve, but it's going through P. In layman terms, that's a tangent. Yeah. Now, the orange writing that I have here says that the gradient at point P is equivalent or is the same as the gradient of the tangent at point P. Yep.
Okay.
Okay. Now, if we go to this situation here, if we take the line PC, so the line going between P and C, is that a tangent?
No.
No, because it crosses the curve and it's very far away. We're not going to have a good time if we try to use that in order to find the gradient at P. If we go to the line PB, now PB is a little bit better, but not very. But still, if we try to use that, it will still be, not a very good approximation of the tangent at P, because it still crosses through the curve. Yeah.
Yeah.
What about PA? PA looks okay. We can do something with that. It's getting really close to, what might be the tangent. Do you agree?
Yeah.
Okay. So the whole idea of it is that we need to choose the first principles of differentiation is choosing a point that is a very small distance away, a very tiny distance away from the point at which we are trying to find the gradient at. We find this point because it allows us to still do our straight line gradient, so change in y over change in x. It allows us to do that, which is still an approximation, but it is close enough to the point which we want to find the gradient at, so that we can use it and find the gradient at any point along the curve. So we could even do it up here. So if this was a point Q, and then up here was a point A, then as long as the line between A and Q looks like a tangent or is almost identical to a tangent, we can use change in Y over change in X to find out what the gradient at that point is. That is the entire premise behind first principles. Okay. So let's do an example just to put what we've talked about into practice.
Okay.
And again, we're going to be using x cubed. Sorry, not x cubed, x squared. So once again, for the third time, I have my x and I have my y. And this is my very rubbish looking x squared graph. So y equals x squared. And just imagine we had, I'm going to use a different color now. Let's imagine that we had a point P here. And we had a point Q there. Now the point P had the coordinates 3, 9. Yep. So we know what the point P is.
Yeah.
Okay. And we are told that Q is a nearby point. And this is the straight line between Q. So Q is a nearby point. Okay. Now let's draw. Before we do anything, let's draw our so-called triangle. What color am I going to use? Let's use orange. Let's draw our so-called triangle for our change in y over change in x. This will be a point R. So where these two lines meet, that will be a point R. Okay. So let's assume that let's say that PR PR equals 0.1. Yep. So the distance PR is 0.1. Yeah.
Okay.
What would be the point R?
Point R.
So the distance between P and R, by the way, it's a perfect horizontal line. The distance between P and R is 0.1. What
it would be, wouldn't it be the y on Q minus the y on P?
No,
change your y over the change.
No, we're not at that stage yet. I want the coordinate of R. I want the point R. Well, maybe I should have said coordinate. I want the coordinates of R.
Q minus P.
Q minus P. Well, Q minus P is this line here. It's the red line. I don't want that. I want the coordinate of R. PR is a perfectly horizontal line. Yeah.
Yeah.
The distance between P and R is 0.1. Therefore, the horizontal distance between P and R.
You have to add. Sorry, you have to add 0.1 to 3, and
Good.
then 9 is the same.
Good. So r is 3.1 and y remains the same. Okay, so let me write that better. So 3.1 and then 9 is what the point r is. And likewise, what do you think the actually we don't know that yet. Do we know that? No, we don't know that yet. Okay. Or do we? So we're trying to find the gradient of PQ. So what equation would we use to find the gradient of PQ?
Changing y over changing x.
Changing y over changing x. So that's going to, so if we do changing y over changing x, so our gradient is changing y over changing x. So what would our change in y be in terms of lines or points?
The changing y.
Yeah, what would our change in y be? What line would our change in y be?
Don't we need the coordinates for q to do that?
We're getting there. We're getting there.
Oh,
I just want to know what line changing y would be.
it will be qr.
So QR over PR is what our change in y over change in x would be. So let me just recap. So we've chosen the point r so that the distance of PR is 0.1. That means that the x coordinate of r is 3.1 with the same y coordinate. Yeah.
Yeah.
Now the coordinate of q is actually 3.1 squared. Why do you think it's 3.1 squared?
I'm not sure. Or is it because y equals x squared?
Very good. Y equals x squared. Okay. So whatever, because this is a y, we're still following what the function is. So whatever x we get, we must square it to get what y is. Because we're on the line. If we were at any random point like within space, then yeah, it would be much difficult. But we're not. We are on the actual curve, so we must obey what the curve is doing. And it says that y is squared whatever x is. So if x equals 3.1, then the y is 3.1 squared. So let me rub this out there. And that's going to be 3.1 squared. Okay, so we've got our points. Yes.
Yeah.
Now we use simple straight line stuff, changing y over changing x. So changing y over changing x is the same thing as QR divided by PR. Now QR is equal to 3.1 squared divided by 3 squared. Yes. Or divided by 9, because 9 is here. Basically, the height of R is 9, but the height of Q is 3.1 squared, which is bigger than 9. So I'm just going to say 3.1 squared, take away 9. Sorry, not divided by, take away. I meant to say take away. Yep. So that's what QR is. That's what the change in Y is. Do you agree?
Yeah, I do.
Okay. And the change in X, what's the change in X?
3.1 minus 3.
Which is
0.1.
0.1, okay? And when we punch these numbers into a calculator, so 3.1 squared, take away 9, divided by 0.1, we get 6.1. Yep, we get 6.1 as the gradient. That's an approximation though, okay?
Okay.
How do you think we could improve this approximation? So how could we get closer and closer to calculating the true gradient of at P? What do we have to change?
The coordinate
Of what?
of R.
Of R, or rather the coordinate of Q. I only did R because it was easier to work from that direction. But the fact remains
Oh,
is that we can bring Q closer and closer to P.
okay.
So
Oh, yeah, that's true.
yeah, in order to get a better approximation, that's probably spelled wrong. In order to get a better approximation, bring Q closer to P. When we do that, what we're essentially doing is that we are creating an expression that describes small changes. Okay, so for the last time, I'm going to redraw the x squared curve. Okay, and once again, this point here, what color did I use? Purple. This point here is P, and somewhere along here is Q. Now, P has the coordinates of x, y. Yep, we have an x value and a y value. Do you agree?
Yeah.
Now, Q, because I've just said that we need to take a small change, because we still want to be able to do straight lines, but we don't want the straight lines to be so far away. Because if the straight lines are far away, then we will have a harder time correctly approximating the gradient at P. What we want is that we want a straight line that is so close to P that it is basically the tangent. It is basically this here. And in order to do that, we need to take small changes. So Q needs to be x plus dx. And y needs to be y plus dy. So the symbol d means, I want to say infinitesimal, but I don't want to use the wrong words in context. So I'm just going to say it's not d, it's delta.
Okay.
Lowercase delta, I think. But anyway, it means very small change. Yep.
Okay.
This thing here, so capital delta, just means change. But there's a subtle difference between this delta, which looks like a triangle, and the small lowercase delta. Small lowercase delta means very small change. Capital delta simply means change. Yep.
Yeah.
So essentially, what we're doing here is that we are finding we are choosing a point that is a very small distance away from the point at which we are trying to find the tangent at. Yeah. And the essence of first principles is basically taking these. So we take these and we substitute it. We substitute it into our expression for y equals x squared. So if our expression is y equals x squared, yeah.
Yeah.
If our expression is y equals x squared for the point P on the curve, because point P is we took a value of x, we squared it, and we got y. Do you agree?
Yeah.
Then what would the point Q be? What would the point Q be? Hint, hint. It's a simple substitution.
Q.
Yeah, Q is a simple substitution. We need to change this y equals x squared to represent what Q is. Reminding ourselves that Q is a small distance away from our values of x and y. So for Q, rather than simply X, we have X plus delta X. So that's another big clue. How should we how should we change this equation to represent Q?
Um, is it x squared plus delta x?
Nope.
Oh, you just squared the entire thing.
Yeah, because this whole thing represents X, and this whole thing represents Y. It's just that they
Right.
are a certain distance away from the X and Y here. So how should I write this?
Uh, is it just x plus delta x y plus delta y squared in a bracket?
Why are you squaring the Y's?
Oh, sorry, just the x coordinate.
So what am I squaring? What am I writing? Let's start
X.
with the Y's. What am I writing?
Okay, y plus delta y
Yeah.
equals open bracket x plus delta x squared, and then close bracket and squared.
Okay. For Q. So when we multiply this out, we get Y plus delta Y equals X squared plus 2X delta X plus delta X squared. Yep.
Yeah.
Now the gradient, if we wanted a gradient, so let me do that. The gradient is change in Y over change in X. The change in Y is going to be Y plus delta Y minus Y, I think. In fact, we don't even need to. Do we need to do all that? Um, okay, you know what? Because Y equals X squared. So remember Y equals X squared anyway. So we have a Y there and we have an X squared. We can eliminate. So if we change either the Y to X squared or the X squared to Y, we can eliminate it. Do you agree?
Yeah.
So let me put because Y equals X squared, so X squared plus dy equals X squared plus 2X delta X plus delta X squared. I can take X squared away from both sides so that delta Y equals 2X delta X plus delta X squared. Okay, so that's our expression for dy. Now, for our gradient, so if we go back to the whole straight line thing, the gradient is going to be the change in x over the change in y. Now, because q is a small distance of y and x away from p, our gradient is in terms of the delta. So it's going to be delta y over delta x. Because if we look back here, q, the only difference between q and p is a small change in x and a small change in y. And if we do the whole shebang of finding the gradient of this line between p and q, it's really just delta y divide over delta x. Do you agree?
Yeah.
Yeah. So delta y over delta x, and we make our substitutions. So that's going to be 2x delta x plus delta x squared over delta x. Um, I'm going to clean up. So that's going to be delta x, then 2x plus delta x over delta x. And I'm going to do that. So our gradient effectively reduces down to that. So reduced gradient. Now there's one more thing we have to do before we can fully approximate the gradient, right? Now, remember what I said about how do we make this more closer to the true gradient at P? What do we have to do to Q?
You have to square it.
No, what should we change about Q to make it more? If we worked out the gradient and we got a
Yeah.
number, how can we improve that number? What do we have to do to Q to improve that number? If I had Q and we worked out the gradient of the line between P and Q, and we got a number, and that number was okay, but we can make it better. What do I have to change about Q to make that number better, to make the gradient better?
3 times it by delta.
No, physically, what do I have to do to Q? Like,
Oh,
what's the
sorry.
difference between C,
You
B,
have
and
to
A?
bring it closer. You have to bring it closer.
So we have to bring it closer. When we bring it closer, what's happening to dx and dy?
They decrease
They decrease. Until when?
until it touches P.
And when it touches P, what is basically dx and dy?
Um,
What number are they basically?
they're basically P. Like,
Okay, but so if Q is basically P, what does dx and
yeah,
dy have to be?
they have to be 0.
Exactly. So the the last thing we have to do, we have to tell ourselves, we get our true gradient when dx tends to 0. It's very important that we remember this. We get our true gradient when dx tends to 0. So for x squared, uh, gradient using first principles is m equals 2x. So to find the gradient at any point along an x squared curve, it's basically 2 times the value of x. So if I wanted to find the gradient, at 3, 9, like we did before. So before we worked out that at 3, 9 the gradient was 6.1, yeah?
Yeah.
And that was using a very rough line and doing dy by dx. Let's use our final version of first principles to work out the gradient at 3. So if P equals 3, 9, using this equation here, what would be the gradient?
Sorry, ask the question again.
If P equals 3, 9, using
Yeah.
using this equation here, what would be the gradient?
3 times 2,
Which is
6.
6. Okay?
Yeah.
And that in a nutshell is differentiation from first principles. Now, the reason why people don't think they need to know this is because, you know, it's when they actually do differentiation, they're almost never going to use this. But it's important to understand where it comes from, where the whole rate of change comes from. And it's based upon using straight lines. You're basically to find the gradient at any point along this curve, you are basically drawing a whole bunch of straight lines. So I'm drawing straight line tangents, by the way. So I'm drawing a tangent there to find a point there. I'm drawing a tangent there to find a point there. I'm drawing a tangent there to find the gradient of the point there. And I'm drawing a tangent there to find the gradient of the point there. And so on and so forth. Yeah?
Yeah.
So that's why it's really important to know where differentiation comes from. Okay. Before we finish, let me actually give you a homework. Very straightforward homework.
Okay.
So I'm going to ask you to find I'm going to ask you to find the gradient of this curve. And I want you to find it at the point 205. Okay, so let me just print screen. I can't print screen it. Let me light shot it. So this is the curve. This is the curve y equals 1 over x. So using first principles, find gradient at point 0.5. So basically the point right here. Find a gradient right there using first principles.